what are graphs and how we do graph ML, where it is applied. So how is not a very important thing here, why is very important. So hi guys, this is Siddhant Saxena, and currently I'm a resident in ISC and working at a US-based firm like the Agentic. Okay, so I work in predominantly I've been working in geometric deep learning. There is a whole field called geometric deep learning in deep learning as well. So this work was done with Meta when I was at IIT Delhi as a pre-doc, and the talk of the title is Task-aware Latent Graph Rewiring. Can robustly solve oversmoothing and oversquashing dilemma. So it sounds pretty wordy, but yeah, like it is fine. We will see how it goes. A bit about graphs. So like maybe a lot of you are new to the graphs and why graph or so like we have been just yesterday only we got DeepSeek's R1 and everything, like a lot is going on in language model space and these things, right? So people sometimes people do tend to ask that, okay, why graph neural network and something, because it is new, right? New to some people, but like field has been growing exponentially internally or so. So there is a pretty large community who do graph neural networks. So this is from NeurIPS 2024 trend. So as you can see that the graph neural network was top 15 most, so like third most appeared keyword there. So in graph neural network or geometric deep learning, there are like multiple things going on. Some things are called geometric GNNs, who work with small molecules, biomolecules, materials, and pretty much computational biology, computational chemistry, and these things. So also like there have been LLMs proposed for similar things, similar problem statement, similar fields, but these things are pretty fast. They are cost compute efficient and like and also like they give very stable and certain results, right? So they are like geometric GNNs are there. There have been like a lot of work in this thing as well. People have been proposing all of these like spherical equivalent GNN, Cartesian equivalent, invariant GNNs, and these are used for dynamic simulation, generative modeling, for protein interaction, and a lot of these things, right? Apart from that there is a whole different field called topological deep learning. So this whole thing starts with images, right? You have text modality, you have image modality. All of these are the kernels over it, or you can say the tokenizer for the text or everything. They work on pretty much basic linear data structure, right? All of this thing is very linear, and it cannot learn. You can say it cannot learn pairwise or more higher order representations in between the data points. So graphs have been everywhere. You can see that Google Maps in so for traffic prediction, right? So traffic simulation and these things for Google Maps, they use graph ML based predictions only. So yeah, like Google Maps, LinkedIn recommendation, Spotify recommendation, TikTok's recommendation, everybody is using GNNs these days for their recommendations. So at least in industry, GNNs have been used quite extensively. And before coming to here, I have worked with Meesho and Snapdeal. There as well. So like we deployed hypergraph based and graph based services in their architecture at billion nodes scale. So yeah, like it works. At least it works. So some people do think that why graph GNNs if we have the LLMs. So yeah. And we have knowledge graphs, and knowledge graphs have been exploited in LLMs as well for a long time, like KGRAG and these things to ground the knowledge of the LLMs. So yeah. Then molecules, so in whole computational chemistry and at least in protein interaction networks, people have been exploiting GNNs for a long time now. There is also something called agentic graph systems, where so LangGraph, right? LangGraph it at least tries to connect the data in data through the nodes, and how your agent can interact in between the nodes by creating a graph, but they do not use any sort of message passing at least. So standard CNNs and RNN architecture, so like it is a very old slide, I guess. from University of Amsterdam. So standard these basic models, or like all of the models which are coming from these basic fundamental models, they cannot work on this sort of data. Now coming through this topological deep learning. So yeah, like it starts with graphs. So that is why geometric deep learning, it starts with graphs. Then you can think of data or modulate the data in higher order structures as well, like hypergraphs, sheaves, simplicial complexes, and like there is a whole variety of these sort of data structures that you can create, and then do deep learning over that. So basic idea is you want to create so you just want to back propagate over any structure so that you can learn, right? So basic GNNs work in this fashion. So this is the most basic equation of how it aggregates and propagates message. So in GNNs there are like, so yeah, the basic thing is how you collect the message from the node. So what is a message? Message is just a vector representation, which is we put a vector representation inside the node, which is the property of a node. Like if you will relate it to recommendations, so user and products, so you just create users feature embeddings and then product feature embeddings, and then you just put it inside the node, and you keep it that way only. And the edges are if whether user have interacted with the product or purchased the product or anything like that. Then you want to aggregate the message from a local neighborhood. So there is an idea of local message passing. The whole GNN thing works on local message passing because they give them an inductive prior of whether you can learn the local structure or interconnection in between the nodes or not. So you just pick up the neighbors from the features from the neighbor and you aggregate in a permutationally invariant way. It just means some product or anything which do not destroy the permutation invariant property. So this is just the aggregation function. You can just leave the aggregate thing and assume it to sum. Okay, you can just sum it, or you can take the max out of it, or you can just do it in some fashion that it does not destroy your structures, the whole structure of the local neighborhood. Then what you do is you update for each node. Okay, so you collect the message from all of the neighborhood nodes, and then you update the message of the node which you are targeting. And it is not so it is highly parallel. Parallel in the sense you do it for the whole graph in one go. Okay, so it is just a matrix multiplication over the adjacency matrix of the graph and the feature matrix of the graph. Then if you recognize any of these guys, right, this is Gregory Perelman. He solved Poincare conjecture, millennial problem, right? So now we are sort of coming towards my problem. What is the problem in this in the whole thing? What we did at Meta and these things. Apart from that, this is also I wanted to I just put it here. This is curse of dimensionality. Okay, curse of dimensionality is if you would like to learn over higher dimensions. If you are, so every data is a very higher dimensional data. Like so, you are pre-training your LLM on a large variety of data. So like whatever your data set is, then your parameters are directly proportional to your data, right? So it becomes very difficult for universal approximation theorem to learn over the higher dimensional data, and that is why the whole field is emerging. Because if you can leverage the geometry of your higher dimensional data, then you can sort of provide an inductive prior to the learning model, so that like you can learn it better, like you can learn your manifold. So it is all about manifolds, right? Universal approximation, back propagation, and these things. Then it comes to Ricci flows. So Gregory Perelman came up with Ricci flows to solve Poincare conjecture. It is a manifold problem where if you will, so it is a diffusion equation. So you can just think it of a heat diffusion over any sort of vector or connected graph or anything. Okay, so it is for manifolds, but you can discretize it. So what is Ricci flows? Just a basic thing here. Ricci flows is if you will apply the Ricci flow over a manifold, what it will do is it will squeeze out the positively curved manifold and it will stretch the negatively curved manifold. So we will talk about positively and negative, what is positive curvature, negative curvature, and these things. So So what is the problem? Okay, so actually let's think about the problem. Why it is important, and what is over smoothing, what is over squashing, and these things. So at least you guys got the idea of how the message is propagating, right? Over a graph, how the message is propagating. It just creates a computational graph of a particular node, and it propagates the message. Okay, so like these are also like graphs, right? These are not manifold, these are just the graphs. You can like think it of a circular graph. It is a tree structure graph, and this is just a grid, right? And these structures are found in a substantial fashion in large graphs. So when you will think it of a graph of LinkedIn scale or Twitter scale or these things, there will be a lot of these structures which are substructures of that graph, right? So there is a problem here in propagating message. So what is the downstream task? Downstream task can be node classification, link prediction. So recommendation engine is just the it just boils down to link prediction task over a graph. Okay. So the point is, if you want to learn anything over the graph, you have to propagate message. Okay, in order to make the GNNs work, you have to propagate messages efficiently. So this whole efficient message propagation comes in the way, because if there is some sort of structure which is something like this, right, tree. So there will be a lot of messages coming from this substructure, and this substructures, right? And you also have to propagate message from this to this, okay, in a substructure of a large graph. Now the problem occurs is when a lot of messages are coming from this direction, there is a high pressure preservation, so high representation preservation pressure on this particular node. Okay, so why? Because it cannot, so vector size is limited, right? Your feature dimension is limited. Whatever the features you can accommodate inside the node is basically fixed. It cannot be fixed, but at least it is finite, right? Like heterogeneous graphs can be, it can have different dimensional features, but it is finite only. You cannot have infinite feature dimension inside a node, or like at least it has not been experimented. The computation thing as well. So yeah, so you have to preserve your representation at this node as well and this node as well. Then this blue node comes in the picture, and this blue edge, right, it is having over squashing issue. Okay, so what is over squashing? And this is negatively curved. So I just want you to quickly think in this fashion only, that okay, wherever there will be cyclic structures in your graph, the structure will be the Ricci curvature, discrete version of the Ricci curvature will be positive, and wherever there will be tree structure in graph, there will be high negatively curved edges in terms of Ricci curvature. Okay, so you can just memorize it, like it does not matter here. You can have a look at the resources. So yeah, negatively curved edges will tend to have a lot of over squashing, and positively curved edges will tend to have a lot of over smoothing. Okay, so both of these problems are sort of connected with each other, because over smoothing is also smoothen out your messages. Essentially the messages becomes nullified, or comes to a particular representation, so it becomes non-representative, like it does not matter what your message is. This is over smoothing, and over squashing is it will not even let the information pass throughout the edge. So this is over squashing. So wherever there will be a cyclical structure, right? It can be a circular, or it can be a grid sort of a structure, or anything like that. There can be cycles of 3 form, 4 form, any sort of cycles. These cycles will tend to have over smoothing, because your message will revolve inside the cycle again and again, right? Because every node is passing the message to other nodes, so the message revolves inside the cycle, and eventually the information gets nullified. So this is called over smoothing. And then this representation preserving pressure, right? So you cannot preserve your representations if your view, or what you can say, the field from where the message is coming grows exponentially, right? So for this node, for this black node, these two structures are giving it the message in one go, right? Maybe I'll also talk about hops. how the hops work, and what is the extension of message you can propagate. But yeah, the main point is this black node will have a lot of representation or information coming towards it. It cannot even pass the information to other black node if it also contains. So basically the connecting edge in between communities, right, in between communities of your graph. So this is a community, okay. Even though you cannot see there are a lot of cycles are here, okay. So this can directly be replicated to a graph as well. So like all of the nodes can be create the whole, so text to embedding to the feature. So this is a community. Let's suppose this contains a lot of cycles, or if not, let's forget about cycles here. Let's only talk about the connecting nodes of two communities, okay. So these connecting nodes, right, so this community will propagate message to these nodes with sufficient stacking of GNNs, of course. This whole community will propagate message to these nodes, and this is also propagating message to these nodes in order to propagate your message from this community to this community, right. There the oversquashing happens. So the information is coming up thoroughly from a lot of nodes, and due to these connecting nodes are very less, and for the cycles your information is revolving inside a cycle. So these are both of them are an issue here, right. And maybe now like you can think that why oversmoothing and oversquashing are connected in a sense, okay. Because okay, so how you will elevate one of these, okay. So how you will elevate oversmoothing or oversquashing? Basic thing is, you can, if you will destroy the cycle, okay, if you will destroy the cycle, then you will elevate oversmoothing. If you will connect in between the tree like edges, right, like this node, if you will connect this node to this node, if you will connect tree like edges, then you are creating more connections to propagate message. So this is how your oversquashing will elevate. Basic idea, right, that you form new connections to elevate oversquashing, and you destroy cycles to to elevate oversmoothing. This is the basic thing. But the problem here is, if you will destroy or add a lot in your structure, then you are basically losing out the structural property of a molecule or of a community or anything like that. So you have to do it very carefully, right. So yeah, there is, so now it comes towards graph rewiring. It is a subfield inside graph ML. So yeah, basic thing, right. The graph rewiring is very intuitive in the sense that you want to rewire your graph, add or delete your edges in the graph, or nodes as well in some fashion, so that you can at least either you elevate oversmoothing or elevate oversquashing or these things. Now what is the literature review? Literature review is, people have been proposing these things like either you can do oversquashing, either you can do oversmoothing, or these things. So this has been a problem in this field, that okay, so why we are talking about graph rewiring, right? So the point is, if you will solve these problems, right, it will directly, so it is a pure problem, and it will directly get replicated to all of the industries, like recommendations as well, like everything will get start solving, right. So solving pure problem, and you can apply it to a applied problem as well. And so the problem was, they were doing graph rewiring in a very rigid fashion, that okay, so okay, if there is highly negative, so one hypothesis is very intuitive, that okay, this is highly negative Ricci curvature, you just add an edge wherever the Ricci curvature is negative, you just add an edge wherever the Ricci curvature is positive, you delete an edge. The basic point is, whenever we apply a Ricci flow over a manifold, what it does is, it recognizes where the Ricci curvature is higher on a manifold and where it is lower, okay. Positive Ricci curvature, what it does is, it squeezes the manifold, and for negatively curvature, it stretches the manifold, so that your manifold becomes rounded, okay, and a bit rounded. And how they solved the Poincare conjecture? Basically, after your any manifold becomes rounded, you can perform surgery over the manifold. So this is very intuitive now, that okay, how you are using Ricci flows or Ricci curvatures to solve the both of these problems, or at least one problem in the graph, right. So even in this paper, they try to only solve oversquashing, right? So at least you can see that this bottleneck is now getting filled up, and you can propagate messages very naively. But it is also sort of over smoothing is getting up right here. So in my work and like the whole Rexis team of Meta, we wanted to have some model so that we find an equivalence in between these two. And this is now my work. So my work is about you want to rewire encoder decoder structures. Like what you can do is you can encode your images, you can encode your text. Similarly, you have graph variational encoders, graph encoders as well. You can encode your whole structure to a latent space, okay, and then you can reconstruct your graph. So what I thought was to work with these sort of models and try to rewire your graph. So what you want to do is you want to rewire your graph in the latent space so that the structural problem is not that particular of issue or what. And we will see the architecture. So we will skip these things right now at least. But yeah, like it is all about inner product operations, okay? Everywhere it is inner product operations. So yeah, this is the architecture, okay? This is the work that I proposed, and the paper is about to publish in TMLR, so it is equivalent to NeurIPS. So yeah, so how it works, okay? So there is one thing called Ricci flows. Ricci flow we already observed, right? So what I did is I created a variation of Ricci flow, which is curvature-sensitive Ricci flows. So it is not that big of a deal because it just applies an exponential function over the Ricci flow, so that you can do Ricci flow exponentially and you can create adversarial structure. So what I am trying to do, how I am trying to find a balance in between both over smoothing and over squashing is this thing. So one thing is above part is for over smoothing, okay, alleviating cycles. Below part is for over squashing, alleviating the negatively curved structure, and there is a huge weight on the task as well. So I am also considering task in my loss function. So now what we are doing, so like this will be very easy to understand because we have already developed a lot of intuition over other things. So GNNs and these things you have heard, right? You can generate adversaries for anything. So now what I am trying to do is I am treating highly negative structures of my graph as adversary because I don't want highly negative as well. So what I am trying to do is I am creating two variations of my graph. One variation is first iteration of CSRF. Another structure is fifth iteration of CSRF. Why 1 and 5? Because till 5 it is already too much negative. You can see like all of the cycles are destroyed. So this is basically VGAE, variational graph autoencoder, and how it works is it first encodes your whole structure and the features. It first encodes into a latent space, and then it decodes or reconstruct your graph using the inner product only. So instead of any complex reconstruction rule as in images, we just do inner product multiplication in between the latent spaces. So that inner product will give you the edges in between the structure. So these are the basic losses. So yeah, so this is where we are computing the KL divergence in between your priors and the latent space. So yeah, now the point is, in order to alleviate the over smoothing, what I am doing is I am finding the cycles inside the graph in the latent space. So we are walking inside the latent space now. So it was a bit difficult to think, and we did a lot of experimentation then, okay, how we can do it, but how you can walk inside the latent space is you can take the initial structure and you can compute the z vector, so like latent vector of those initial initial structure, and then to walk or to find the neighbors, you just have to compute the basic inner product in between those two, so if the inner product is higher, so there is a higher probability that okay, there is an edge in the structure there, okay. And this is hierarchical CSRF, adversarial CSRF, how CSRF is changing. This is simple Ricci flows, and what is the LaGRAR. So LaGRAR is my proposed model, how it is changing the the edges, the distribution of edges over the topology. So main property is task specific. It is dynamic in the sense that it do not uses your initial computational graph of your whole model. It computes or changes the computational graph dynamically, in the sense that every epoch it is changing your loss function, right? And it is solving the oversmoothing and oversquashing dilemma. So results were pretty good actually. On node classification is nothing, it is just like your semi-supervised node classification, where you have your node features, user features. If you can think it of a fraud detection thing, okay. So whether some user is doing fraud or not, 0, 1. So the classes in your whole graph will be 0, 1, 0, 1, 0, 1, and your nodes will be nodes will have their own features of how user is behaving on your platform. So this is how the node classification task works. Link prediction is recommendation, and graph classification is your protein based or molecule. You want to classify whether your molecule is coming up in a particular class or not. So this is graph, an example of these things. There are like a pretty standard data set on which you can do experiments, and you can like, so for graph rewiring the whole field, they have given a lot of data sets, and they are standard in the industry and research as well. So what we have done is we have done extensive experiments on different class of graph rewiring approaches, and I have skipped some details, but these 4-5, right, these 4-5 baselines are hardcore rewire. They perform hardcore graph rewiring either by spectral or by spatial message propagation. So I have skipped some nitty-gritty details over those things, because they do not matter in this talk. And apart from that, this GAT. So GAT is very basic thing that everybody can see whenever he looks at the whole graph neural network. Your attention is also something which rewires your graph implicitly, okay, and it is task specific as well, because when you apply a GAT or stack a lot of GAT layers, you solve your task, but attention sort of puts up a weight on an edge, so like attentive weights on the edge, so that your message gets propagated on a weighted edge fashion. So yeah, like these are my models, sort of class of models that we have proposed, and we got better results on. And apart from that, one more thing was, none of your rewiring technique was able to solve all of the graph tasks, like node classification, link prediction, graph classification. Either they used to do link prediction, either they used to put up node classification or graph classification. So what we proposed, a very generalized model which can work on everything, okay. So like graph classification as well, link prediction as well, node classification as well. How link prediction? Because graph variational autoencoder, right? So the whole point of GVA is link prediction only. So this is how leveraging GVA in our method will give you results on link prediction as well. So yeah, like thanks. I'm SidGraph on X, so please hit me. Thanks.